All right, so starting up with question number 8. Question number 8 is not a calculation question. It just asks for two conditions that would basically determine whether carbon-14 is appropriate to use. And so the first thing that I wanted to make sure that everybody realize is that carbon-14 can only be used on samples that are younger than 50,000 years. The reason for that is the half-life value of carbon-14 to carbon-12 is very small. It's only 5,730 years. So, for example, if we had to date dinosaurs 65 million, that would be 65,000,000 divided by only 5,730. The number of half-lives would be really, really too high and not really manageable. So we've set a limit, and we say that we can only be used on samples that are younger than 50,000 years. The other thing is that carbon-14 can only be used on things that are alive and were once alive. And they are the two conditions that we use. I think that's the only problem on this page. Yep, so I'm going to switch now to question number 9. It says, explain why it is not wise to use uranium-238 and lead-206 to date a fossilized dinosaur bone. Keep in mind that the half-life for uranium-238 is 4.51 billion. That is almost the age of the entire Earth. And that's the time that it takes for just one half-life. So if you were to consider dinosaurs, and if we went back, even if we went back, let's say to 70 million years is nothing in comparison to 4.51 billion. So not even one single half-life would have occurred on a dinosaur bone. And that's the reason why that's not an appropriate pair to use for that particular test. On to question number 10. It says, given that the half-life is 0.7 billion years, what is the age of a sample if 1/16 of the starting material remains? Okay, so we're going to use this fraction to figure out how many half-lives have occurred. So there's one half-life. There is two half-lives. There is 3 half-lives, and there is 4 half-lives. So we know that that's 4 half-lives. The time that it takes for one half-life is 0.7 billion. So what we're actually going to do is we are going to take 0.7 and we are going to multiply that by 4. So 0.7, here we go, 0.7, multiply that by 4. And we just determined the age of the rock to be 2.8 billion years. On to the next problem. This is a good problem because we can see quickly 2,000 grams. So hopefully by now that people realizes that any time that you're given grams, you're immediately going to set up a parent-to-daughter ratio. And it says that there were 2,000 grams of radioactive element, and it radioactively decayed, and all that we actually have left right now is 125 grams. So this is a case where we have to determine how many times do we need to divide by 2. Well, 2,000 divided by 2 is 1,000. 1,000 divided by 2 is 500. 500 divided by 2 is 250. 250 divided by 2 is 125. So that was 4 times. So the parent isotope got halved 4 times. So now we can determine the age because we know the time for one half-life is 0.4 billion years. So all we're going to do is we're going to take 0.40 billion and we're going to multiply that by 4. So 0.40, and then we're going to multiply that by 4, and that comes out to be 1.6 billion years old is the age of the sample. Moving on to question number 12, it says, how many half-lives have elapsed if 1/256 of the original parent remains? So here we go. 1, 2, 3, 4, 5, 6, 7, 8. So the answer is 8 half-lives have occurred. Moving on to question 13. A bone from a woolly mammoth that was pulled out of permafrost contains carbon-14 and nitrogen-14 isotopes at a ratio of 1:63. So as soon as you see a ratio of 1 to 63, you know that the fraction is 1 over 64. Even if we look above in the in question 12, we can figure out the number of half-lives. So 1, 2, 3, 4, 5, 6 half-lives have occurred. So using that, we now know that we had 6 half-lives. Now we know the time that it takes for 1 half-life, so we're just going to simply multiply that by 6. So if we were to take 5,730 and multiply that by 6, we will come to an age of 34,380 years for the age of that particular sample. Now, moving on to question number 14. How much potassium-40 will remain in a sample after 9.1 billion years? Now, this is not a question that you need to really worry about on the public exam because there's not enough information here given. So they're giving us the age 9.1 billion. So we're going to take 9.1 billion, okay? Now, that's the age. So typically what we've been doing is we've been dividing the age by the half-life value. And the half-life value is 1.31 billion. And I know that potassium-40 goes to argon-40 with a memorized half-life of 1.31 billion. But again, that would be given to you on the public exam. So we're going to go 9.1 divided by 1.31, and that's essentially going to come out to be 7 half-lives. So they want to know how much potassium. Well, we can give it to them in a fraction. The question didn't ask how. So we're going to go 1, 2, 3, 4, 5, 6, 7. So we could say 1 over 1/28 of the original amount of potassium-40 is left in the rock. Moving on to, I think, the very last question on this particular worksheet. It says a rock sample contains 75 grams. So as soon as we see grams, we're immediately going to set up our parent to daughter ratio. This is a little bit of a different one, though, because you got to be careful how you read it. 75 grams of daughter. A common mistake would be to put 75 grams under the parent, but that's not what it says. It says 25 grams of parent to 75 grams of daughter. You divide both sides by the smallest number, so that's going to give you a ratio of 1 to 3, which is a fraction of 1 over 4, which gives you 2 half-lives. Knowing that the half-life value is 40,000, and we have 2 half-lives, it's going to be 2 multiplied by 40,000, so we know that the sample is approximately 80,000 years old. And that is the end, I am pretty sure. Yes.